EDM or micro EDM? Almost everybody is doing it. Good. So I don't have to talk very slowly. And those who are not doing micro EDM, I don't know how many of you are interested in it, because I assume they are all interested in diamond turning or diamond milling and so on. So I can quickly, basic things of EDM, I'm sure you know. I will not take much time. I'll go quickly because time constraint is given. I'll have to finish by 1 o'clock. I have a lot of things to talk about. Tomorrow I see how much I can cover. And again, for a joke, Professor Jose Matthew, if you cover everything this time, he may not call me again, so I will leave something for you to read, to study. But I'm always available, you can communicate with me. I do not want to rush to cover so many things. So, elite grinding is left, but I will try to cover that very quickly. Elite grinding is also very interesting. At least you should learn the principle of elite grinding. Oh, sorry. Okay, I'll talk about basic principles of EDM. I'm assuming that all of you know about basic principles of EDM. It is nothing but creating discharge between the electrode and the workpiece. And rest of the things, and this discharge, actually, it is old concept. This is the electrode, and this is the workpiece, and there is dielectric, which is liquid. Dielectric is, when charges do not flow. It is deionized medium. Okay, so, and this gap, this is the detail here. If I cover all these details, it'll take time. I will quickly, if you have any question, you discuss with me, but basic thing is that this is the EDM system, this is the workpiece, this is the electrode, discharge is given from here, and in the gap, since it is a dielectric medium, when the gap becomes very small, and energy accumulation is very large, and a plasma channel is created. And discharge at this plasma channel, the temperature, people did not actually measure it, it varies, changes from, it's between 8,000 to 12,000 degrees centigrade. So a spark takes place, breaks that medium, and spark is generated, and that causes localized erosion of the workpiece material. Okay? So this is not very clear. So these all the details are given here. No, depending on their polarity, there are. If you have no question, of course I should not raise it. Usually the polarity is changed depending on which one you want to erode, the electrode or the workpiece. Correct? So positive pole is considered to be sacrificial electrode. If you put the positive pole to the electrode, it will wear off more. If you put it to the workpiece, then workpiece will erode more. So I think with that introduction, we move on. And when at high temperature, localized spark takes place, erosion takes place, the material gets vaporized. So vapors come out, and when the on cycle it happens, in off cycle, the bubbles all disappear. And the material which is produced, which are not completely vaporized, becomes molten and solidifies after with using quenching function. And our responsibility is to flush them away, and some of the things cannot be flushed away, they stick to the electrode. Sometimes electrode, sometimes to the workpiece surface. If it sticks to the electrode, good or bad? Bad. Because? Yeah, but good thing is that everything is good and bad. You have you can have secondary erosion and spark because of that. So that way you may be able to remove more material, but it is not good because ultimately we want the accuracy. Okay, all these definitions and so on, I should not tell you again, correct? You know about all this. Those who do not know, you please go through the notes, you will see. Because my time is limited, I want to cover the interesting part. Okay, all these things I have already said. That polarity, don't worry about polarity here. The polarity is given to the positive polarity is given to the electrode, and this is the workpiece, negative polarity is given here. And as the gap increases, the voltage increases. Here, the ampere, if you look at it, this side is increasing, voltage that side is increasing. Okay, so slowly gap reduces and voltage increases, stabilizes at that point, and then current starts coming in the picture. Current slowly increases, and when it reaches the maximum, then the sparks takes place, and that causes evaporation, and all these vapors are accumulated here, collapse of the heated vapor gas, and termination of discharge, displacement of the melted tool and workpiece. They are usually flushed out. Some of the molten materials keeps floating, stick to the workpiece or electrode. Okay. This situation is on cycle, after that comes off cycle, okay, and it repeats. So some controversy don't. Here you see the crater is produced, though it is negative polarity, maybe this softer material, that is harder material, that could be the reason. And then this whole surface becomes rough. Again, when the next on cycle, all the tips are attacked and they get eroded, it may even go down further. So that way the surface becomes rough basically. The electrode also wears off. And these are the molten particles left on the surface or in the surrounding. And again, next cycle, it starts from the peak and slowly it spreads. Okay? So these are all this. Now, each pass occurs between the closest point of the electrode and the workpiece. And from the closest point, it goes deeper and deeper. Now, this is interesting to note. When I say it is interesting point to note, the students in the class, indirectly I tell them that is a point to be asked in the exam, but here it is not exam. I am suggesting you to take it as a topic of research. Okay? Sparking occurs in a frequency range of 2,000 to 500,000 sparks per second. So if you know the energy of each spark, then you can single spark, then if you know if so many sparks are taking place, then how much energy is generated, correct? Now this remains, this uncertainty 2,000 to 500,000, where you will draw your limit. Those things, back calculation from energy, you can find out actually how many sparks took place. And when it is more or less, you need to find out what is causing the more sparks, what is causing the less sparks, correct? So this is an interesting point. You can go back to any energy equation. From there, you find out, applying like analysis, find out actually how many parts are. So that would be very interesting to find out. And then you can develop an analytical equation to see what is the amount of material, and again, what is the amount of material on the electrode, on the workpiece, why it is so, how hardness is affecting it, how the power, voltage and current is affecting it, and all these things. You saw yesterday when Dr. Afzal was presenting, he was arcing And arcing, imagine voltage is, the current is so high, correct? And current and voltage is so high, this is not like this EDM. So the target was to remove tremendous amount of material so that we can compete with normal drilling. And we on top of that normal drilling of inconel, 8 millimeter diameter, 2 millimeter, 1 meter long with an accuracy error of 0.1 millimeter is almost impossible. And using that method we can do it. We can have high amount of material removal, yet we can achieve the accuracy desired. So, and I think Afzal did not do the energy calculation. So all these things you can do. There are plenty of unknown things in EDM area. And on spark on, electrode and workpiece material vaporized. Every discharge or spark melts a small amount of material from both of them, depending on where is the polarity and what is the hardness. So you can even thoroughly study what is the effect of changing the polarity. Is it only the surface finish and material removal rate, or is there any other effect? So those things you can quantify, you can easily write papers. And don't take a simple journey. When you do a research, think always what it is going to give me. Is it me too, or is it something new? And if it's something new, small or big, take the challenge. And I think I've quoted many times Einstein's quotation. How many of you have listened to me? Einstein said, engineers create things which had never been. So Einstein thinks that. So we'll have to do new things to remain relevant to the community, to research, and to everything, to our job. The vaporized material is positioned in the spark gap between the electrode and the workpiece in what can be described as cloud. These are simple things. And this is the cloud. Spark off. Vaporized cloud suspends in the dielectric fluid. When the spark is turned off, the vaporized cloud solidifies. I've already told all these things, that they stick to the electrode or stick to the surface. The efficient machining, the EDM chips must be removed from the sparking area. Please remember that. So how we can remove this? What should we do to remove all these debris? By flushing. And removing them is best. If you cannot remove them, what do we do? We don't allow recast layer. If we want to flush them away, but we cannot flush them, like Afzal's case, if he had no flushing device, what would have done? For him it was difficult because the workpiece is too heavy. But usually UDM pieces are small. You use a vibration device to vibrate it. That means keep the floating objects unstable so that they cannot form the secondary electrode. Okay? Or they cannot stick to any of these things. If they stick, helpless. So that they cannot stick to it, just keep them vibrating the workpiece so they remain floating. Yes?
Gap is changed now. Sparking gap is
yes,
continuously changing by applying the vibratory motion.
Sparking gap changes.
Because in EDM the sparking gap is play vital role, right?
No. Okay. Servo will take care of it.
Okay.
Servo control. Every
Okay.
machine has servo control.
So simultaneously the electrode is also vibrating?
No, electrode is not vibrating. Electrode is the spindle which is very heavy. Workpiece is vibrating.
Okay. So vibratory assisted EDM, na?
The response is very fast for the servo control, yes, please.
Okay, I don't know about that thing, so I am
The servo
asking.
takes care of that. Yeah. So I didn't go into the old video. All these things are in this slide, but time constraint is because compound EDM and ECM would be very interesting to listen. That is not in the textbook. Okay. And Rajurkar, again, all these things what I said, he put it in one diagram. Initial gap, the gap closes and spark begins, plasma grows and the gap becomes very narrow, the plasma becomes very large, then evaporation takes place, explosion takes place, and molten materials come out or vapors come out, flushing is to be done, and another spark comes in. The previous small graph I showed, that is by Kunieda, this is by Professor Rajurkar. EDM system, yeah, here comes this thing, servo control system. Two things actually. This is the servo control system to take care of the gap for sparking. And this is the generator, the whole thing. Yeah, this is where EDM is taking place. Okay? Basic elements, I think this is already shown. Dielectric reservoir pump, power generator, working tank, excitable, tool holder, servo system. Same thing. Now, there are two types of circuits. One is RC based, resistance and capacitance, another is transistor based. Okay. All the details are there. I'll try to cover quickly. Time has become my enemy now. Basically, our machine currently is RC based. As you see here, this is the capacitance, and it slowly builds up, and then current goes up. At that point, spark takes place, then again starts from zero, voltage goes up, current goes up, and sparks takes place. So and here the stray capacitance is utilized, which is very small quantity. Benefit of this capacitance or small amount of voltage is that it erodes small amount of material, then finish is very good. Our target is to get very high finish surface. We are not bothered about large amount of material removal. But getting demand from the customers, universities don't argue about it. They are happy because they want to do it for research. Now we have come out with a EDM power supply which covers large, which is based on transistor as well as capacitor. So if you want to do very fine machining, you keep it RC circuit on. If you want to do large volume machining, you make the transistor circuit on. And you can keep both on depending on amount of material removal you want. And what we are trying to do, what we are trying to establish is that the machine should be able to do machining from fine, small amount of metal removal to large metal removal. I'll show you I think I have a chart to show what is the difference between RC circuit and transistor circuit. We have very soon our new EDM power supply will come, where you can have small volume, fine finishing removal, or large volume, fine finishing, because it has both the circuits. Okay? RC type relaxation type, it's called relaxation type. Earliest type of pulse generator can generate very small discharge energy using stray capacitance, used for finishing purpose for micro EDM. And this is the RC circuit, resistance and capacitance. The voltage and current I have showed you. Generator, this is the way it is done. Voltage and current characteristics of RC generator are given here. Small but fluctuating voltage and current amplitude. And transistor based circuit. Okay, so a transistor is field emission transistor type of pulse generator. So this is very fixed and amount is large, can precisely control the on time and off time, provide higher discharge energy, thus provide higher material removal rate, used widely in conventional EDM. So what we are trying to develop, bring them together. So Prof. Jose Matthew, don't be anxious, we will give you the new power supply if you want. no. I didn't like to make it public, but since he's asking me, no, it is not free. But you will get a special discount because you are an existing user. Okay, okay. No, and your support is tremendous. We really admire your support. Publicly, I can tell you, one of the best support I get from NIT Calicut. So all these details I leave to you. I should not dwell on it. Transistor circuit details are given here. And transistor circuit beauty is that transistor circuit is more stable and quite deterministic. RC circuit is not deterministic because we are not removing large amount of material, small amount. RC circuit is good enough, fine finish, super fine finish. I'll show you later we can get nano surface finish using RC. Whereas for transistor, you cannot get nano surface. Okay. So, voltage and current, you've seen it is all very fixed value you get. These details, okay. And again, it depends. You can get normal discharge or abnormal discharge. So you should be very careful while designing. Okay. T on pulse, T pulse off, T pulse on, and high frequency, low power for microEDM. Okay. So this way, you even for transistor circuit, you can design it to give you low power and high frequency. Okay. So these are all features. Okay. Workpiece material, any conductive material you can use, but does it mean that you cannot? All these old concepts are changing. Can you do EDM of non-conductive materials? Sir, you can do it, so you know it. You need to do some doping. Dielectric fluid is, so when you use dielectric fluid, please look at the working condition. Don't go for kerosene and vegetable oil without analyzing the ambience, without analyzing the working parameters, correct? You may end up getting fire. So, if electrode material also, harder the basic principle is that harder the electric material, less will be the wear. So better to go for harder material, but on the contrary, then workpiece material will be rough. But if you want workpiece to be fine, then you use a softer electrode material, so that you have more wear in the electrode, less wear in the workpiece, because you are doing fine finishing. Of course, the next thing I will talk, then you don't have to worry about that. Dielectric fluid flush point should be as high as possible, and viscosity lower the viscosity, better it is. Specific gravity, lower specific gravity is desired. Process parameters, you will decide based on your requirement. Planning type, so you will have to plan the operating parameters, and machining condition, you will have to have monitor the sensing, you will have to sense the parameters, and finally you will have to have, based on your performance parameter, what you want, finished surface, more material, and so on and so forth. Okay. Now let me come to the microEDM. Okay. So I'll cover about basic principles. Basic principles are same as EDM. Difference being in the size of the tool used when microEDM comes, the power supply of the discharge energy, the resolution of the axis movement. And here, I'm sorry to say, when I started selling our machine, I had lot of resistance, lot of my junior colleagues from different institutes, I won't name them, they were saying, why you are selling such an expensive machine? Why can't you make a cheaper machine? I said, depends. If you try to get a cheap machine, the performance will be cheap. But I do not want to sacrifice the quality, because you are doing research with it, and microEDM research. No, our student needs to understand the basics of EDM. Then why do you buy a micro EDM machine? You buy a conventional EDM machine, very cheap, then you teach them what is EDM. And if you teach them EDM, fine, you are feeding them to the industry, they will be happy, industry will say, oh, they know. But at the end of the day, they do 1 year research project on EDM, and at the end they go to the industry, they say, what have you learned? I can teach you in 6 hours. So why did you spend 1 year to do your project? So what the industry has, if we teach the same thing in university, then what they are going to contribute, because they can employ a polytechnic graduate and they can do the job. So you'll have to carry something with you, claiming that I have learnt it in my institute. So that must be ahead of the present technology. So that's why you will have to, hopefully you need to learn, you will have to invent a new EDM process or something new which is much better than the existing technology. So in that case, if you are in the name of micro EDM, you are buying a machine which is not at all micro EDM. Now, as I told you, micro, we debated about it. Micro should be micro accuracy and micro feature. Now, I was in recently in one of the universities, 3 students came and asked, sir, I want to make micro ECM electrode. And I said, what machine you are using? So he told me, what is the accuracy? Plus minus 5 micron. That means error of 10 micron. And what is your size of electrode? 10 micron. So are you getting 0 micron electrode or 10 micron electrode? So, and one student, I visit IIT Jabalpur, and one student came from far to discuss with me about micro EDM. At the end I said, what machine you are buying? He said, this is the machine. What is the accuracy? Plus minus 5 micron. So I said, why are you buying that machine? That machine is so lousy. No. What is the difference? Why should I pay 2 or 3 times for your machine? I said, fine, good luck. So you should have the feel. In the case of measurement, we usually say, if you want to measure 10 nano, your measuring device should be 10 times more accurate than that. Exactly, when you want to measure a feature or want to generate a feature, your machine should be preferably 10 times more accurate than that. Okay, beyond that it will become very commercial talk. Let me skip that. So, difference between, I'll come to that. Size of the tool is important. Power supply, that's why we went for RC circuit to give very low power. And resolution of the axis, here I stop. Resolution of the axis should be very high. If you are trying to get a positioning accuracy of 1 micron, your resolution should be 1/10 of a micron. If you are trying to get 10 nano, your resolution should be 1 nano. If you want to get 1 nano, your resolution should be less than 1 nano. And somehow, by positioning feedback control, you can improve it, but at least what accuracy you want, the resolution should be smaller than that. So basic things, please try to follow. Okay, this is a comparison of what are the machining, micro machining processes which can, manufacturing processes which can give defined here. I think I should not dwell on it. It is just for your own comparison. 6 slides are there. You can have a look. Not very important. Okay. Now, if you put them in chart, dimensions and aspect ratio, I put them all together. Where we stand? Micro EDM, dimension usually from 1 to 10 or 15 micron or even more, and aspect ratio we can go up to 8, 10 and so on, which is not true. Now we can get very high aspect ratio using flushing device and so on. Okay? So in the past, when this graph was written by Professor Dr. Masaki long time back. Okay, ECM comes here and comparison. Oh, it is not very clear. conventional EDM and micro EDM. Okay? Size of the tool greater than 1 millimeter, and it is less than 1 millimeter. Inter-electrode gap 10 to 500 micron, and for micro EDM less than 10 micron. Open circuit voltage 4 to 400, and for micro EDM 10 to 120. Actually, in our case, our voltage goes below 10 volts. Yeah. And high side also ours is low, but now we are covering from 1 volt to 120 volt. Peak current greater than 3 ampere, and in case of micro EDM less than 3 ampere. This also we are playing with parameter less than up to 10 ampere. Pulse on time 0.5 to 8, and for micro EDM 50 nanoseconds to 100 nanoseconds. Specific energy is very high in conventional EDM, and for micro EDM it is very low. So these are the basic comparisons. But if you can cover both, then it is still better, which we are trying to do. And some of the features, if you look at, this is conventional EDM, bulky parts, and when it comes to micro EDM, you look at the dimension. As I showed you already, 6.5 micron diameter on steel plate, aspect ratio is more than 8. And this fine electrode is made by wire EDG, I showed it earlier. These are the cases. And usually for conventional it is done by, it could be done by EDM. Most of the cases it is done by milling. Electrodes are made by milling or turning. Okay. So there are various processes: die sinking micro EDM, micro wire EDM, micro EDM drilling, micro EDM milling. I think I don't have to elaborate on it. Micro EDM techniques, we have already discussed some of it. Block EDM, turning micro EDM, wire EDM, wire EDG, wire electrode discharge grinding, where we shape the electrode using wire EDM. Milling micro EDM, that is very important. Yes, please.
Excuse me, sir. I am Deepak from NIT Calicut. Sir, I have a doubt. Sir, while making that 6.5 micrometer hole, sir, since that electrode diameter is so thin, won't the flushing causes bending of the tool? Is there a chance for that? The flushing, I mean the electrode in our machine, in your machine, the nozzle is actually flushing the dielectric to the spark gap, directly to the spark gap. So won't that affect that tool since it's just 6.5, around 6 micrometer diameter? Won't it cause a bending?
Yeah, it didn't cause bending because you are not flushing at very high pressure. Flushing was flushing. Yeah. Yeah, sheet was very thin. Moreover, we did not do, yeah, sheet was very thin, and 6.5 micron hole, electrode diameter was 5 micron only, and flushing was not flood flushing, and the plate was a very thin plate. It was sunk inside, and it was quite fast. Bending on it didn't take place. You should not be flooding on it.
No.
Any question?
It
Yes.
was dipped inside.
Professor, I have actually no idea about this experimental site, but
Yeah.
I would like to know one thing. When this melting fluid, whether there is any impact of rheology on the fluid? Is there, I have no idea. Whether there is any like a materials where rheology is different, like fluid rheology, or always it is a Newtonian fluid?
Fluid rheology is different. What we mean by that, frankly speaking?
Like a your
change the property.
stress and rate of strain. What is the relation actually for the fluid?
What is the...
Like a linear relation you have, or any non-linearity also there? Like
no, this is, it is so localized,
yeah.
Nothing happens. Flow, rheology means flow.
Yeah.
No. Actually, we have not analyzed, and I'm sure it doesn't happen.
Okay.
A good question.
No, I do little simulation only. But
Oh yeah, you're from mathematics.
yeah, but one day it's
Good.
why always we have the melting fluid has the Newtonian properties? That was just one day I was thinking. So is there any workfish and this process? It makes like a change. The rheology is very complicated in some cases, or always people use Newtonian model.
A Newtonian model, and you develop the model first,
Yeah.
and then bring in all these factors to verify, to see with the experimental performance. That is better. Rather than initial model should always be very simple. From there you proceed. Now I remember your background. So you start with a simple model, bring in more and more complicated factors, which will be very useful. My honest request. And those questions you are asking, very good question, but we have no definite answer to it. Only we can give answers based on intuition. If anybody has any answer, please volunteer.
Just few points. I mean, you said about the rheological properties. In order to change the rheological property of a fluid, basically you need to have that much concentration of any other added material. Now, for example, in this case, we have the dielectric. Okay, so it's really a Newtonian fluid. It's not that viscous to start with it. And when the erosion happens, if you just look at it's a spark-based, it's very localized. The amount of material that is getting removed is a fraction. It is a part of a debris as well as the molten material. So since it is a localized, either it is getting just solidified at adjacent region, or some part of it is getting flushed away. So if you just look at compare with the gap, the quantum of the dielectric fluid actually moving in, so it is a very, very fraction of it. So rheological properties is not a major concern, but the electrical properties, that is a major cause of concern because of this debris, molten material, the plasma, some gases getting evolved, because most of the dielectric fluids are hydrocarbons.
Yeah.
So that leads to gas formations. So major worry for any microidiom or maybe even conventional idiom is a change in the thermal properties of it. And rheological but of course, as we approach to the micro to the nano,
Yeah.
maybe perhaps we get the nano controller and nano pulses, and in that case, if we are in a position to control that one, then in that case, if the gap is getting very small and we are not able to escape those molten materials, then that molten material will itself exhibit what you are saying is the rheological behavior.
Most importantly, it is so localized, it doesn't affect the surrounding. Thermal, otherwise, if you imagine at that sparking point, if temperature is 8,000 degrees centigrade, meaning lowest one, if it is not localized, it could be full of fire. So, most important thing, initially you can just ignore saying that effect is negligible. Then your analysis will not be affected, I am sure. Then, when we go for microidiom, there are various ways milling. Okay. Uniform wire medium method, how to maintain the uniform wire of the electrode, CAD-CAM development for microidiom, 3D micro machining by microidiom, micro nozzle fabrication, electrode making, assembly, measurement, and so on. And so many topics are there. You can pick up any topic to do. I'll try to cover some of them. Block idiom we have already discussed, correct? We should not dwell on it. This is more details of the block idiom. You have seen these diagrams. All these things, examples. And we did, by block idiom, we quickly fabricated the electrode, and for fine finishing we use wire EDG as well. So we got these things, examples. And this is by wire EDG, you get a fine electrode, with that you can get. And this is another example of wire EDG to fine machine the electrode. So these are all examples. And on machine electrode making by wire, So all these things we'll skip quickly. And microedium milling. So usually it is for die sinking, but you can do microedium milling as well. You can generate a surface and you scan the surface, you continue to move, and there are various, when there are steps and so on, how to control the gap. So these things, you can pick up a research topic and continue on it. Applications by microedium milling, we generated a feature I have shown earlier, small pyramid, and it is 25 micron, width is also, bottom is 25 micron by 25, pyramid is 25 micron by 25 micron at the tip, height is 35 micron at the top, and step size is 7 micron, and it is done by microedium. So all these things can be done, NUS written, and this is Spinneret, one Chinese company bought it, they want to flow their thread while making textile. Uniform wire EDM and normal EDM wire takes place like this, and then you can control it you can do some, every time in off cycle you do some machining and bring it to the fine shape, and you can, this way you can have, when you do milling, you continue this path, don't come back, you reverse the path, and this way you can overlap the path to make it more uniform. So these details are there. There are various ways of reversing, straight reversing, and longitudinal, horizontal, and so this way. Layer 1, then for next layer you come this way, reversal of the path. So these are all details, you can read the notes. Should I go slow or should I just quickly finish? Nothing much to learn. And for 3D objects, what you do this zigzag path, this way or that way, patterns of XY paths. These are techniques, applications. One car body was fabricated using this uniform wire of the electrode. These are all applications. These are for making an electrode. Okay. CAD-CAM, I should not talk about CAD-CAM. You'll have to have generate CAD data, then converted them into CAM data, and I think one of my students, Dang, developed a software for it. So it's all 3D microEDM. These are the examples. I quickly skip. And nozzle making, this is proposed by Professor Masuzawa, I think. Yeah, Masuzawa, Tokyo University. Finally, he gets the mold to make needles. From there he makes micro nozzle, and commercial machines are there. This I can skip very easily. Oh, by the way, Panasonic, they are no longer making machine, they are using our machine. And Cyrex, Panasonic doesn't make any more machines. Good thing they are using our machine, Cyrex machine. And micro tools machines you have seen, I'm not going to repeat here. Now this is interesting. I think quickly I touched on it. EDM is supposed to be a rough process. You can get micron accuracy, but our challenge was to get nano accuracy. Right? So have you heard about that? In EDM you can get nano accuracy, nano finish, mirror finish. I think I have given you the background. Did I tell that one of the Japanese guy, Masaki, who was working in Panasonic while they were selling the microEDM machine, theirs is also based on RC circuit. So he was doing microEDM, and he got his PhD from Tohoku University, and he got his thesis ready, got his PhD degree. He came to Japan with his wife to give me a copy of the thesis. And so I was very happy. So the guy was very interesting. He says, Prof, I've come all the way to show Singapore to my wife and give the thesis to you. I said, I was very happy, thank you very much. But Prof, I have something to request you. While I was doing EDM, I saw bubbles coming out. I said, it could be vapors. He said, no, sir. When during off cycle, even after stopping EDM, I see bubbles are coming out. So he said, you want me to give the answer? You want to do another PhD? He said, no, sir. Then I said, I will not give you the answer. Can I get another PhD project? I'll acknowledge that problem I got from Professor Masaki, Dr. Masaki's thesis. Can you guess, if I'm not told you, can you guess what I thought, why the bubbles are there while he's doing EDM? Sorry?
By the electrolysis process,
Electron,
hydrogen bubbles are formed.
hydrogen is coming out. Bubbles are coming out because when ECM, you do ECM, bubbles come out, correct?
Due to electrolysis process.
Yeah, due to electrolysis. So I thought ECM is taking place. But EDM is basically done in deionized. For our case, we do mostly in water. It is done in deionized medium. Correct? Ions are not supposed to flow. But why we get bubbles? How come ions are flowing? Because why? Why in EDM we see ionization is, bubbles are there. So I got the answer immediately and I gave it to a Vietnamese student, a very brilliant guy, Dang, and I told him, can you do EDM and ECM together? Same thing, he said, sir, it's impossible. How can you do? One is deionized medium, another is ionized medium. And people do EDM first and do ECM to do the finishing. So they change the liquid in the bath, clean it, and then they put ionized medium. Or they carry it and take it to another machine to do it. So ECM itself is very slow, EDM is slow, ECM is further slow. So if you can combine them together, again in one machine you can do it, your investment is less cumbersome, you don't have to change the liquid, you don't have to clean the machine, you don't have to have two setups. So very reluctantly he said, sir, since you are saying, I will do it. If somebody has heard this topic, how many of you have listened to my topic, compound EDM and ECM? Oh, so then you know it, okay. Those who do not know about it, for them I quickly say, everybody actually, today or tomorrow my pomegranate breaking, tomorrow, okay. So this is something, when you do everything we take, like turning, everybody thinks longitudinal turning. Nobody thinks about step turning. So EDM, everybody takes it granted that the medium is deionized. Nobody thought it may not be 100% deionized, because deionization, you carry out deionization. So when the student was arguing too much with me, I said, hey guy, are you sure when you do EDM every time it is 100% deionized? Oh no sir, sometimes if you forget this deionization machine, then there will be some ions. So I said, why don't you do something? After 100% deionization, you continue and stop the deionization process, you continue your EDM, and you continue to measure the deionization level. He continued EDM, and when he saw that when ionization reaches 78%, below that he cannot do any EDM. So that means you need at least 78% deionization to carry out EDM. So that means you can do EDM even in ionized water, but the ionization should not be more than 18%, 22%. Clear? Then I said, okay, you forgot about EDM. Do your ECM. See whether you can do ECM in 100% deionized water. Then you continue to ionize it and see at what level of ionization you can do ECM. And he says if the medium is around 18 to 20% ionized, then you can do ECM. Does it give you the clue? So if your deionization is about 80%, then you can do both. Now how will you do both? In on cycle, you do EDM. When in off cycle, no EDM is going on, ECM will be done. Correct? So on cycle EDM, off cycle ECM, same cycle, and at the end you get a surface, EDM surface ending up with ECM. Simple. All these things I'll just tell you now with more facts and figures. Now having said that, and he started very happily, he was getting partial nano surface, then he struggled on and on and on, finally he got complete nano surface. So these are the fine tuning. Concept is clear. If you use partially deionized medium, you can do EDM and ECM together. Basic. But to get nano surface, I'll take you through the journey. Those who have listened to me, please bear with me. And this paper, when I told you, I think, when I submitted in CIRP, they accepted it, not believing it can be done. So the chairman of the committee was Professor Rajurkar, secretary was Professor Kunieda. So they were happy, and Dr. Kunieda stood up and said, Prof. Rahman, being a scientist or engineer, today he will be a magician, but he will prove a magic can be science or science can be magic. Let us see how he does it. So this is the journey. So he thought it is, what I said is not right, but so analysis, drawback of microEDM, rough surface due to overlap craters and heat affected zone is there. So sequentially what we do microEDM and followed by microECM. Changing machining fluid, which is problematic, combine in the same process different machining fluid, you change the fluid. So what he did, approach is microEDM is in dielectric fluid, microECM is in electrolyte. So one is non-conductive, another is conductive. Okay? Can we compound them together? The clue is that low resistivity deionized water. That means you find out what should be the resistivity. So dielectric strength is strong enough so that spark can occur, which is that 78 to 80%. Slight conductivity, which promotes weak electrochemical reaction, okay, ECM. So that's the clue. You can do simultaneous EDM, ECM milling, which is called SEDCM, simultaneous EDM and ECM. So the clue is low resistivity deionized water and short pulse. If you remove lot of material, then finishing will take long time. During pulse off time, your finishing will not be completed. So short pulse, so that dissolution is localized. A small amount of material is removed. Low feed rate. You allow the feed rate to be slow to allow enough time to get finished, okay, to promote electrochemical reaction. So these are the clues, facts, and you do vertical feeding, and then you continue your milling. Okay? After vertical feeding, you continue your milling. Okay? Medium milling. And this way you proceed, dissolution takes place, and then go to the, you give horizontal feed and go to the next cycle. So this way you continue from here to here, to here, to here, here to here, then you go direct there, come here, and continue. Okay? Then I give you the results. Initially, scanning feed. Feed is 50 micron per second. This is the case. This is the case 30 micron per second. And third case 20 micron per second, 10 micron per second feed rate. When you have very large feed rate, surface is rough because you have not given enough time for ECM action to take place fully. 30 you see some finished surface, and then you see bigger finished surface, and finally you say almost complete finished surface. So the clue is the feed rate should be slow, and crater size should be small, low material removal rate, slow speed, two things, and low resistivity deionized water. Okay? Low feed rate is a prerequisite for electrochemical reaction. And short pulse. Please remember, you will have to have short pulse. If you have 500 kilohertz, and if you have continuous pulse. If you have continuous pulse, dimensional error take place, surface is bad. If it is short pulse, then surface dimensional accuracy is maintained and surface finish is very smooth. Okay? So it should be localized dissolution zone. Layer depth should be small. If you have 1 micron, surface is not very good. If you have lower depth, 0.5 micron, surface is better. So smaller layer depth, another condition to be fulfilled. Then fabrication of different types. This is different shapes you can do. Again, whether you do it at feed rate of 50 micron per second or 10 micron per second. That makes a lot of difference. 50 micron per second, complete only EDM taking place, and if it is 10 micron per second, EDM plus ECM is taking place. Now, to get the concrete result, at 50 micron per second, short pulse, normal pulse, then you get very rough surface, and CDM with 10 micrometer per second, short pulse, you get complete nano surface. Just looking at the surface is not enough, you look at the graph. The red line is this one, only EDM taking place. When both EDM and ECM taking place, is the blue line. If you see the concrete data, simultaneous EDM and ECM, better surface finish, up, how come? Results are not written here, sorry, it's an old slide. This surface roughness is, the values are not written here. Believe me, it is correct value is red line, surface finish is 142 nano. For the blue line, it is 22 nano. You get complete mirror surface when you do EDM and ECM together. How come? Okay. And for short pulse and slow speed, you get good dimensional accuracy as you see it. And heat affected zone is removed by electrochemical reaction. Thank you very much. I finished before 1 o'clock. Any question, anything?
Good afternoon, sir. On machining micro holes using micro EDM, how to remove the debris particles apart from using that vibration? Is there any other technique?
Flushing device?
if I am going for a larger depth, how the flushing particles will, whether it will be removing the debris particles, whether the fluid will be passing over that clearance between the electrode and the workpiece.
I didn't get the question. Rakesh?
No, sir. How the flushing will be working to remove the debris particles between the clearance area, between the electrode and the workpiece. So it may be in microns. Whether the fluid particles will be entering the region, sparking region.
So he's saying that the gap between the tool and the electrode is very small when you do micro hole drilling. So how will you remove those small particles in the small gap?
Okay, one is the vibration device.
Yes.
Another is how small is your hole?
Suppose if it is 50 micron.
50 micron. Okay, if it is more than 100 micron, I request you to use pipe electrode. Flushing is, you can control the flushing pressure and all the debris will be washed out.
Okay.
If it is small hole, I think you'll have to go for vibration. And now vibration, as I told earlier, we are using low frequency vibration to keep the secondary electrode, that means the debris floating. But now we have found if we use high frequency vibration and they are more unstable, which is better. So it is better to use smaller the hole, higher the frequency. And efficiency tremendously improves. That is the only way. Otherwise, if hole is more than 100 micron diameter, then go for pipe electrode.
And
Thank you, sir.
just to add to what Professor said, people have used orbital motion of the electrode also. So since you are saying the gap is very small, so what they do is they use the orbital motion of the electrode so as to increase gap on the other side. So it gives space for the debris material to come out from the bigger gap.
Yes.
So that also you can try.
Orbital motion you can use, but then hole size will be slightly bigger, so you'll have to compensate that. How much is your orbital motion, and then what should be electrode size, so that you get your targeted final correct shape.
Thank you, sir.
Yes, you can change the feed rate, of course you can.
No, dielectric pressure. Dielectric pressure. Fluid pressure.
Fluid pressure in the tank or
No, it is at constant pressure.
okay. If it is, it comes with flushing device, then you can change the pressure.
If you change that mechanism, you can vary that pressure, fluid pressure,
Yeah.
so that you can remove the debris
Yes, yes.
according to the conditions.
Yeah, that is the way. But if it is not flushing device from external flushing you can try, but if it's a very small hole, whether the flushing will be effective or not, outside, external flushing, pressurized fluid, it is worth trying, definitely.
No, but the problem is, sir, in that case, if you apply external pressurized flushing, the electrodes are very thin. Electrode
may bend, electrode may vibrate. And if you could apply flushing, uniform flushing pressure around the electrode from all sides, then it would be okay, but I don't know how to.
Well, I mean, I'll share my experience with the flushing. I mean, it is more problematic in case of ECM.
Yes.
Of course, we have more debris here in the first case. In ECM with the electrolytes, we can actually play with the debris. They can be made dissolvable. In EDM, we have more or less molten or the solid kind of debris. But when you apply flushes and the flushing direction, from it is entering from one side and it exits from the other side, that actually affects the accuracy. It has something to do with the maybe discharge action or the electrolysis action. So I have been observing this consistently, that entry point and exit point, you will always see the differences into the dimensional accuracies. So it's not just getting rid of the debris or byproducts, it is also affecting your basic fundamental process. So you need to experiment, just like there are various methods of flushing. So whether it is getting interfered with fundamental of the EDM or the ECM. So you can, even if one can easily experiment it, you don't try with the micro tools, perhaps you try with the bigger tools and try to see how the flushing actually varies, maybe your dimensional or the roughness at one end and or the other end.
Yeah.
So that is again one more critical factor.
And when you are using external flushing, how do you, again, on top of that, how do you ensure that flushing is uniform all around the hole? Because you will be applying flushing from one side. Yes. I heard about it, but somebody raised the hand. Same question? Yeah. Magnetic field. Yeah. 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 And somebody tried some other way. I won't tell the name. So he had a something like cap on the device and sucking out the debris. But this problem of sucking out debris is sucking out the dielectric itself. So at the end, after doing a lot, very confidently he did his research and said, "Sir, I have got an improvement of 10%. I said, "Why did you spend 2 years to do this work to improve 10%? The student was very upset. He was not my student anyways. So when you do something, you should be thinking your targets, what you want to achieve. Is it doable or not? Sucking out debris, you are sucking out the dielectric. Yeah.
Okay, sir, shall we?
Yeah, for me fine.
There's no recording now.
But they have to 10 more minutes if you want to.
There's some other thing.
Programs are there on the modeling. So we would, and Saturday mostly will be some other activity, and only possibility is tomorrow. Is it possible to start with some problem and how to do the assumptions and how to go with the analytical modeling so that we can teach better to our students? Anyway, it's a request if possible.
Let me answer this question. I knew, I had hunch that I may not have time to go for modeling. That's why yesterday I gave you 2 examples of modeling. I hope you saw. Objective was that I'm covering a topic, introducing modeling. That would be a practical one. Was it? Did you follow that? Yesterday's presentation was actually simultaneous, modeling and analysis and some innovation.
I think
if I have time, I can give you another model on high-speed machining. These are case studies. That is the best way. Excuse me for that, because I knew that I may not have time. So that's why diamond turning was supposed to be 1/2 of the day. I took actually 1 day and a half, 3 sessions. Please excuse me for that. If I have still time, I will go for another high-speed machining with modeling. That is very elaborate. But if I do not have time, please bear with me. Yesterday I concentrated on that actually.
I think your expectations may not be over with 1 or 2 days. See, that complete modeling, starting with that, it takes a lot of time. And for that, we have to look at the journal, the basic journal. And one journal is not sufficient. You have to refer that. All things cannot be completed. But what Professor yesterday was trying to convey is how to create that inquisitiveness, bring that and give the problem to the students. And further, it is up to them. Use equations and how to club these equations and modify that and do it. Other than what do you expect, even the students, sometimes our students also ask, sir, give us that they want the complete worked on model and do that. That won't work. So I think that may not happen, but still, Professor, I hope you can give that if time.
1 minute. I repeat what I summarized yesterday. When you have a problem, try to analyze what are the causes of this problem. Try to remove those causes to come to the solution, or solve those problems to come to the solution. To solve the problem, look at the factors. What are the factors causing the problem, like deflection of the beam, force and length of overhang. So that way you identify the parameters and try to look for an equation which mathematicians have already done, which fits into that problem. If something does not assume that factor, which is close, fit it to the, based on that equation, then go to finite element analysis, see the result matching or not. If not, your assumption is wrong, change the assumptions, change the factors, and this is one type. When there is no fundamental equation available, go for geometrical modeling, looking at the parameters, experimental results, experiment you do, from the experimental results, you see like cracks, depths and so on. If you read Arif's thesis, you'll see how he developed the geometrical modeling. So it could be analytical model mathematical, it could be geometrical model, it could be empirical model. But empirical model based on statistical analysis, my honest request to all of you, never ever go for it. Statistical analysis gives you the trend, it does not tell you the cause and effect. So that is not a research. Sorry to say, that is Taguchi. Please get away from Taguchi, come to Taniguchi, because Taniguchi says micron nano accuracy, and let us have the decision of the GIAN course group says it should be further down, could be pico accuracy. And the year you decide. Let us have another meeting to decide by when, 2030 or, okay.
Okay, we'll wind up. No. See, I just want to discuss or get feedback from you. One is, I got some requests from